All right. This time we're asked to find the intersection of two functions. Now, before I do anything, I try to think about it, take a look at it, and see what's coming, see what I should be expecting. And when I look at these two functions, I notice that the largest power of x on each one of them is 1, which means these are linear functions, these are lines. And so I'm really just looking for the intersection of two lines here. Now, I know as soon as they ask me for an intersection that I'm looking for, my answer is going to be an ordered pair, right? My answer is going to have an x and a y value to it. And so that's something to remember as I keep working here, because I'm going to do a lot of work to find the x value. And it'd be really tempting to think I'm done with the problem when I found the x value, but I'm not. It's actually asking me for the point where these two functions cross. And that is an ordered pair. It's not just the x value. It's both the x and y. All right. Well, if I'm looking for the intersection between two lines, let's just draw two random lines here. So if I draw one line here and I draw another line here, the thing about the intersection that is true is it's the point that is true for both equations. And so if I take this x value, kind of my xs for solution, my ys for solution, and I run that xs, ys, or that xs through this function, I'm going to get ys as my output. And if I run xs as the input to that function, I'll get the same ys for my output because this is the point that exists on both lines. All right, now that was just a for illustration, so let's erase that because it really has nothing to do with our numbers. What are we trying to do? We're trying to find the point where the outputs of both of these functions are equal. Well, that sounds a lot like f of x equals g of x. Well, that looks a lot like 3 times x plus 1 equals 5 minus 2 times 3x plus 4. Okay, well, let's distribute that 3. So I have 3x plus 3 equals 5 minus, and what's keeping me from getting at this x? It's the same reason I distributed that 3. What was keeping me from getting at that x was the parentheses. So I got to get rid of the parentheses. And so I'm going to distribute this -2 through those parentheses so that I have access to that 3x. Of course, it's not going to be 3x anymore. Now it's going to be -6x. And that'll be -8. Okay, so now I have access to that x, and I have access to this x without any parentheses around them. So my goal is to get all the x's on one side and all the constants, all the numbers on the other side. So how can I do that? Well, it seems like adding that 6x to both sides would be a really good idea. Because if I add 6x here, that equals 0 and it goes away. But if I do it to one side of the equation, I better do it to the other side of the equation. Okay, well, my next goal is to get rid of the constants from the left-hand side of the equation here. And if I subtract 3, well, 3 minus 3 equals 0, and so that would go away. But if I do that to the left-hand side of the equation, I better do the -3 to the right-hand side of the equation too. All right, now let's see how this works out. I've got 6x plus 3x, that'll give me 9x. That equals, oh boy, now I got 5 minus 8 will give me a -3. -3 again will give me a -6, right? Now, I want the x all alone. I want a 1 in front of that x. Right now, we have a 9 over 1. I want that value to equal 1. The only way I can do that by division is to make that a 9 over 9, because 9 over 9 equals 1. 1 times x is just x. Then my x is all alone. But I can't just go dividing the left-hand side by 9 and let that be it. Whatever I do to the left-hand side of the equation, I also have to do to the right-hand side. So now I have x equals -6 over 9, which is close but not quite good enough, because that's the same thing as saying negative 2 times 3 over 3 times 3. And my 3 over 3 there equals 1. And so what I really have is 1 times negative 2/3. And so my x value is actually negative 2/3. Now, if I underline that, make a box around that, turn it in, I sadly don't get full credit, because I haven't solved the problem. I've solved the hard part of the problem, well, what I think is the hard part of the problem, but I haven't solved what I was asked. I was not asked to solve that equation. I was asked to find the intersection of those two functions. And that, like I said at the beginning, is an ordered pair. And so we've got half the answer. We've got the x values. The way to find the y value is to just take this x value and plug it back into either one of our original functions, or both if you like. You should get the same y value out for either one. So plugging it into both and getting the same y value out is a nice comfort that you've done it correctly. All right, so reclaiming some of my white space there. Let's try it. So if I do, let's choose a different color. If I do f of negative 2/3, that will give me my y value. And so that's going to be 3 times negative 2/3 plus 1. Remember, to evaluate a function, we just replace the dummy variable in the function. That variable that holds the pattern of our function, we replace that with whatever value goes in the f of, the parentheses next to the f. We call that the argument of the function. Okay, well, that would mean that f of negative 2/3, if I simplify this a little bit, I'm going to distribute that 3. That's going to give me a negative 2, right? Because the 3's will cancel. And then that'll be, oops, it switched me to an eraser. Then that'll say plus 1 times 3 will give me a 3. And so f of negative 2/3 is going to equal 1. And so I know that my answer, what I want to put in a box here, is negative 2/3, comma 1. And that's what I would report. Now, we can make ourselves feel a little bit better a couple of different ways. We could try calculating g of negative 2/3. What's that going to be? That'll be 5 minus 2 times 3 times negative 2/3 plus 4. That's why we change colors, because we're running close to our other calculations. All right, well, the 3 over 3 is 1. And so 3 over 3, that cancels, because it's 1 times the negative 2, and it just leaves me with the negative 2. All right, and so I still have my 5. Now I'm going to distribute that negative 2 through all of those. Negative 2 times negative 2 is going to give me a positive 4. And then negative 2 times a positive 4 is going to give me a negative 8. And so I'm literally going to get 9. 5 plus 4 is 9, minus 8 gives me a positive 1. You give negative 2/3 is a positive 1, which is good, because if it was anything else, we would have kind of a contradiction here, because the whole point of this is that at that x value, the y values are the same, because this point exists on both lines, on both functions. One last way to comfort ourselves and make us feel a little bit better about this would be to graph it. So if I go to y equals here, and this y0 of x is just like my first function and then my second function. I can keep going. I can put as many functions onto this graph as I want here. So my first function was 3 times x is going to be my variable button, which is next to alpha. That x, t, theta, in button between alpha and stat. All right, so that'll be x and then plus 1. That's my first function. I should, most modern calculators will do implicit multiplication, but I should go ahead and put in a star there. It's more clear that way. It's more clear to the computer. And math is all about removing ambiguity, and especially older calculators and many programming languages are very straightforward. If you don't tell them exactly what to do, they will not do it. All right, and so now let's type in my 5 minus 2, and then we'll do times, open the parentheses, 3 times my x, and then plus 4, because that was 5 minus 2 times 3x plus 4. Yes, that was my function 2. Now, if I did this math right, the intersection is going to be pretty close to the origin, right? So I probably don't need a huge coordinate system to see this well. So let's do like a minus 2 to minus 2. I think that's probably enough for this window. So if I clear this out and do a minus 2, clear this out and do a positive 2, minus 2, positive 2, and then I hit graph here. What's going on? Uh-oh. What'd I do? Let's go back. I think I know what I did. I go to my Y window here. Yeah. I disabled the plot for the second one. And you can do this on a standard TI-84 with this particular program. This is called Calc84, and it's a very useful app. There's 2 of them with the same name. I think one has a space and one doesn't. They're both very good apps. They both have free versions and paid versions. I use the paid version because I use some of the extra features, but for most students, you wouldn't need it. On an actual like TI calculator, the equals sign would be highlighted if you were graphing it. You could put your cursor over it and hit enter, and it would take the highlighting off the equals sign. And that's how you enable or disable a plot. So in something like this, you enable or disable a plot by clicking those. On an actual TI, you would highlight and hit enter on your equal signs, and that would enable or disable the plot. All right, so now let's go back to our window because I completely messed our window up. Say negative 2. To 2, negative 2 to 2, and hit graph. Oh, good. Oh, good. We actually have a solution this time. And as I'm looking at where it is, the solution, the x value looks like it's about 2/3 back from 0, between 0 and 1. And it does look like they cross right at the 1 value there for my Y output. So it looks like we did our job right. If I zoom in, I can make myself feel even better about that. What else could I do here? There's a button called intersection here. And from my intersection, it just automatically calculated that the intersection between these 2 lines is at negative 0.6, repeating because it's all 6s and a 7 at the end. And then comma 1, which goes along with negative 2/3, and then comma 1. If your calculator doesn't have an intersect button, what else could you do to figure that out? Because not all calculators do have the intersect button. Well, what you could do is you could take one of these equations, since at this point these values are equal, right? If I took one equation and subtracted the other equation from it, that value would be down at 0. Let's take a look at how that would work. So what I would do is I would go in here, and we'll go ahead and disable rather than remove Y1. We'll go ahead and disable Y1. But what I'll do here is I'll then go, rather than just do that equation, I'll say minus, put parentheses here, and I'm going to type in the entire equation for my Y1. So I'm going to have 5 minus 2 times, then open parentheses, 3 times, oops, said it right, typed it wrong, 3 times x plus 4. And you always, when you're done typing, go back in and make sure you typed in what you thought you did, because I have what I call fat finger disease, and it hits multiple buttons at once. All right, so I got 3 times x plus 1 minus parentheses 5 minus 2 times parentheses 3x plus 4, and then close both sets of parentheses. I like it. I like it. And we want to use basically the same window we did before, the negative 2 to 2. The reason it's resetting is because I have this bad habit of using the touch screen on the iPad and panning around, and that changes all those numbers. All right, so now if I hit graph, what I expect is rather than the intersection of two lines, well, I'm only plotting one line, right? I'm only telling it to plot the one line. So I'm going to see one line, but it's going to cross the x-axis at the intersection point for our other graph. So if I do that, that's exactly what I have. And so I can do my calculate a 0 and use my left value as, give me a keyboard here and some numbers, and not a big fan of this keyboard, -1, and then we're going to go over to right, and it's like, no, I don't want that decimal, and we'll just use 0 for our upper value. And if it asks you for a guess, just use your right value as a guess. And now you see how it tells you it's doing this is called a brute force solution. It's doing some numerical methods to more efficiently calculate where this is just by testing numbers rather than by doing algebra. And that's why we call this a numerical solution or a brute force, because it's not really doing the algebra, it's just trying a bunch of numbers. Fewer than you'd think because of the algorithms they use, but it's still just trying a bunch of numbers. But that -0.667 repeating, that -0.6 repeating, is the same thing as my -2/3, and that lets me know, it's a check that my math is correct. So it's kind of nice to be able to check yourself with the graphing calculator. Especially if you're on an exam and you're allowed to use a graphing calculator, it's nice to be able to verify that your math was right. All right, I hope this helps you.